Nice. Thanks everybody for being here. This is a real privilege for this group, and we're happy to be here. Just a quick story before we get going, since this event is named after Wagdy. The first time I met Wagdy was about 30 years ago. I was working for a manufacturer, and the project we were working on had a water performance test of 20 pounds per square foot, which was steep for the time. And of course, we missed it as we did the job. So I flew out to meet Wagdy and try to convince him that it was a little bit over the top. I think you can guess how that went for me. The moral of that story is read the specification, and I know what you're getting into. But anyway, it's just a quick little story that I remembered about Wagdy. So my name is Keith Lindberg. I work with FreMarq, and today we're going to be talking about facade retrofits and the energy performance increase that you can see as a result of it. This is the panel. I'll let them introduce themselves. I'm not Todd, but I do work with Todd, for Todd, and he couldn't be here today, so I'm pinch hitting for him. So forgive me if I say something I shouldn't. No, it'll be all right. Why does the envelope matter? Why do we want to look at it? Well, a lot of money is lost through the lack of performance when it comes to the building envelope. And as we heard in our feature presentation today, almost half of the buildings in the US, commercial buildings, were built in 1980 or before. So they all use monolithic glass. So of course, if you were to bump those up against the codes today, they don't even come close to meeting them. The other thing is if you get into a renovation and you're just upgrading the HVAC system, if you have a poor performing glazing system, you're fighting that upgrade. So it goes against what we're trying to do from a green standpoint. The other thing that I think is underestimated a lot is the environment inside the building. The comfort for those who are inside that building really needs to be addressed as well. So what has our industry done thus far, the glass and glazing industry? We have seen a lot of improvements in the glass, high performance glass. We see very good coatings with high performance levels. We see a triple glass. Peter talked about VIG with some of the problems with the edge of glass. There's issues with that a little bit, but the center of glass U factor is very, very good. And there's other glass out there, thin triples, thin quads, that are becoming a little more popular with really good U factor. So we've seen a lot of money spent on the technology around glass. But the frame, not so much. We just learned about fiberglass, but there's obviously limitations with that as well. So one of the things that we've tried to do at FreMarq is really close the gap. So kind of a hybrid between the fiberglass and the aluminum products. You get the flexibility of aluminum with a thermal bridge that really creates a dam. It doesn't allow the heat to escape that product. But you get the flexibility of aluminum extrusions, allowing you to create contours and create depth, and to give you a visual aesthetic that's different. So, when we do that, this is a fiberglass thermal barrier. It's a fiberglass pultrusion, and what it does is, like I said, it creates a dam. And you can notice that we're covering the entire inside of that frame, which is where that dam is created. So we get some very, very good thermal performance as a result of it. It's used in new construction. Today we're talking about retrofits, so we're going to talk a little bit about the retrofit side. We have used this product. It's not new. It's been around for a while. We have new unitized projects that have been done in the Boston area. The Chelsea Soldiers Home, Holyoke Soldiers Home, and then the Heights in Haverhill. Those projects utilize this technology. Today we're going to talk about the retrofit. The other point I want to make before we move on from this slide is what this allows us to do is utilize 1-inch IG units where standard curtain wall would require triple glass. So there's a cost savings associated with it, and what we'll learn today is there are exponential benefits to using a product like this as you consider upgrades to the building. The retrofit pathways, one way is to replace the existing frames, allows you to bring things up to code. You get the structural integrity of a new, long, durable system. And of course, it gives you complete customization of that system and doing what you need to do in the building. Reglaze is much less cost than total replacement. So, but it allows you to get really good thermal performance values. So there's cost savings associated with it, and we'll see some of the benefits of those today. So I'm going to hand it over to Pat now as he talks about a project where replacement was done at Penn State.
Thank you, Keith. So I'm Pat Spoden, architect with Flad, and the project we're going to talk about is our level 7 patient unit renovation at Penn State Health. And switch hands here. So just some images of the finished rooms. We're going to do a quick introduction of each of us as we get up here. We'll talk about the existing conditions, some of the analysis we went through, the different systems we looked at, the evaluation of the mechanical strategies, the energy savings, and then some thoughts from Dave here, our owner's rep, on just the experience and the overall project and what it means to Penn State Health. So again, Todd is not here, but I've had a probably 20-year relationship with Todd. We've worked on a number of projects over the years. I have not worked with FreMarq on a project for quite a while with their new products. I worked with Todd when he had more traditional curtain wall systems, but was super excited to hear him get into the high performance systems with the Fort Max system. So when this project came up and we were asked to do an envelope study, pulled Todd in, and Matt and I worked with Todd. We all presented to Dave and others at Penn State Health on this project. So that's the story we're going to tell. So, Dave.
I gotta get up a little bit here. Dave Barton, I'm the Vice President of Facilities for Penn State Health. We are a 5-hospital system, and this is our academic medical center, roughly built in the 60s, 611 beds roughly on the medical center side, and then we also have Penn State University College of Medicine. So this is the building that we were working in. Our census was always high, especially for adults. We needed proximity is everything when you're locating patients in a hospital, and we needed adult beds in this vicinity. So this was where our NICU was. So in all of our logic, we decided to put a 3-story vertical expansion on our children's hospital for a new NICU, and then renovate this space for adult beds. So that's what brought the project together. This was an addition in, I think we have it up there, 1987. It was mostly funded by the Commonwealth of Pennsylvania, so you can imagine the quality was perfect. And we didn't even probably know all the challenges we had until we engaged this group and they helped us out.
So here's an image of the renovation, the floor plan of the adult ICU that we ended up putting together. 24 beds, nested toilet rooms, and mirrored hand rooms. But we had to upgrade the envelope with all these changes at the perimeter because we're going to have new areas of spandrel glass and other things. So once we started talking about needing to do an envelope study and figure out the right solutions and the budgeting for it and everything, we wanted to do that early enough in the project because it wasn't in the original budget to do it either. So we wanted to get a good team together. I had worked with Todd before we called him in. And in February of 2019, we really started the envelope study, went out there, did a lot of exterior conditions assessments, got some data. Matt and his team started looking into, some of the existing conditions as well from a mechanical standpoint. We're putting 2 new air handlers on top of the roof too. This is at the top level of the hospital. So the sizing of those new systems was driven by what we're doing with the envelope as well. So from February to May, we kind of ran through all of our options, made the decisions, and then kept the documents moving, construction, and then it was opened in June of 2022. So it's gone through 3 winters already, and we've heard great things so far. So the variables, the one we highlighted at the bottom was really the most important one to all of us, was improving the occupant comfort and the thermal comfort of these rooms. There were a lot of thermal bridging issues around the perimeter of that existing building. The design, we'll show you in some of the sections, there were some interesting conditions that led to a lot of thermal bridging. The window systems were way beyond life. We really needed to think about, how we're going to do this. And then all the different metrics that Matt and team and the architectural team evaluated. We are showing the two main options that we ran through. We also looked at triple glass, but it didn't pan out to be cost effective. And with the FreMarq system, we really didn't need to go to that level to get the performance we achieved with the option 2, our thermally enhanced window system. The cost savings going to the addition of triple glazed glass really didn't make sense from a budgetary standpoint. Anything else to add on this?
What I'm going to add here, and it probably is a good transition to the next slide regardless, is the dew point analysis and how critical that was to deciding where we would land with the solution. Anyone who's a healthcare facility designer in the room would know that ASHRAE 170 is the ventilation standard set through facility guideline institutes. And really, for intensive care unit patients, we're looking for higher humidities in those spaces to improve patient pulmonary function. Even if you had no clue, what that was before COVID, you knew after COVID. Everybody understood. If we can increase humidity, we can help those patients breathe better. So just pointing out that we had that as a challenge to our dew point analysis. Higher humidity levels, especially in the wintertime, we were shooting for 40% relative humidity at a minimum to improve those patient outcomes. But here, between Pat and I, just talking about the layers of the cake, if you will. The fenestration's relatively small, and I think you'll see that in some of the pictures when we get there, but it still accounts for 30% of that envelope. And a lot of things always happening at that perimeter, of course. From an HVAC perspective, the existing system had, as typical, a perimeter air-driven system. You see that casework on the left side. Actually had a nice little slot diffuser in there, like you would normally see. It does treat the window, but it doesn't really condition the space very well. So.
And one thing I did want to point out, it's a little hard to see on the kind of isometric of the floor plate where the ribbon windows were. All of these windows have 24-inch radius corners as well. So one of the first questions I had for FreMarq when I asked if they could, come in and help our team explore options, would your system with the pultruded fiberglass stem be able to be radius on those corners? And initially Todd Frederick went, no, it can't, but give me a little bit. And within a week, he came back and said he tested a new material that would be able to be radiused, so that he transitioned from his traditional pultruded stem in the straight sections of the frame to a new material at the corners, and then they're welded together. And we had a solution that we could explore. It did add a slight, increase in cost initially to this floor, but we've since renovated the entire third floor, and that cost of that extra extrusion has now been paid for, and FreMarq has a system where they can do pattern glass corners with their system. So it was great that we had a partner who was willing to immediately think outside the box and then just tell us, no, it's not possible. But some of the conditions that I wanted to point out, this was a steel frame building, but it also had these big downturned concrete encased edge beams, so a lot of concrete. The insulation was way on the inside. There were some things we couldn't do. We weren't going to remove the 4-inch thick limestone and address some of these odd conditions. They also had infill CMU below the tube steel frame, a 4x6 tube steel below the windows that was there to support the 4-inch thick limestone. The CMU is non-load bearing. So we'll show you in some of the thermographic analysis later, and all that insulation then was on the inside of that 6-inch CMU. So the slab edges with those downturned concrete beams and stuff got pretty cold, and the floors were conducting a lot of cold into the building as well. So we looked at insulation types like everyone's talked about. In the end, we did decide to go with with a spray foam, class 2 foam, and we'll show why again in the thermographic analysis and some of the issues with the detailing, why that was helpful. But we looked at a bunch of options for the opaque wall areas of the building.
Yeah, Pat, I'll take over from here, and then to give you the no signal, so let's move on. So just very quickly, standards we had to apply. Everybody knows these standards. Hash rate 90.1 is setting the energy standard since basically 1989 when the commercial standard was generated. But unique to this project, Pennsylvania IECC at time adoption was 2015. So we ended up with a window system U value driven by IECC versus the wall assembly, which was driven by hash rate 90.1. Let's go to the next one then. And just to point out a few things here, this is option one. Generally speaking, the curtain wall system with the upgraded wall assembly sort of being Captain Obvious. It works, the diagram on the right, but it's a little clunky. It's a workable system, but it has a radiant heat panel in the ceiling to mitigate that condensation on the window. And then you do get, still a good bit of transfer of cold air, through that curtain wall.
So I'll switch to option 2, which is the thermally enhanced frame. We were able to eliminate the radiant panel heating system because their frame and the glass perform so well that we're eliminating the dew point and condensation potential there. This is the option that we ended up going with. And I think the next slide actually, this is another image of the product we use with that thermally broken frame. The slide that I think tells a lot is this slide, option 1 on the top right of the screen. And that's the curtain wall, but relying on radiant panel. You can see the frame temperature is still, at 47 degrees on that winter day. The option 2, we were able to keep the isotherm line fully in the sprayed insulation that we put on the back side of the limestone. We removed that 6-inch non-structural CMU, which was just creating a really deep edge for the cold to conduct through the slab edge into the building. We wanted to get the insulation further out, make our real clean transition. We actually even played with the line of the glass and got the primary seal directly to the limestone. The old system had the glass back another inch or 2 and it relied on a flashing below the window system. Also dealing with those curved corners. We wanted to say it was a cost-conscious decision, but also performance. So everything we looked at, we were trying to just get the best optimal performance with the budget we had for the project.
And yes, that is a 10-degree difference on that sill, which is pretty impressive. So how did they afford this? It's interesting because I wasn't going to start with this on the slide, but budget, Pat had mentioned, it wasn't budget. There were no envelope upgrades, in the project when Penn State Health initially sent out the RFP. But through the process, we sort of proved that, you really can't afford not to do this. The two options we talked about so far, at the end of the day, what really drove the needle for option 2 was the removal of that hot water radiant panel system. And we've heard this all day long. If you can minimize the HVAC systems, you're going to save energy, over a lot of time, of course. But again, the biggest needle movers here are decreasing the HVAC system by 22% overall. It's about a 50% reduction in cooling load. But again, to the right, all the way at the bottom, removing that hot water radiant panel system is the biggest driver to cost savings. And again, just a quick summary of all those things, but the thing I want to point out here that we haven't before is really removing a system to maintain and the benefits of that from an owner's perspective. Every facility engineer that I talk to tells me, Matt, just give me one less thing to maintain because I don't have the people to do it for the most part, but I also don't have access to do it. Good luck getting into an ICU patient room to fix something in that space. Patients very critically ill, they're hooked up to all kinds of equipment. Nursing staff is everywhere. It's like the impossible thing to do is get in those spaces. So I think that's another really important comment to make here. I think there's more cost analysis on the next slide. We could probably just skip this. This just shows the overall HVAC layout. 2 new air handlers that Pat had mentioned, left and right wing. So the central piece in yellow is an existing system. Even though we didn't replace that system, it still saw the same benefits. The reduction in cooling load, reduction in airflow. Relatively small piece, but again, even your existing systems will see those benefits. First cost, talked about this a little bit already. Overall, for the option 2 system, saving about $350,000, mostly due to the extra $200,000 from the removal of our radiant system. But something we'll touch on, maybe in the next couple of slides too, is how can you afford not to do this? Removing that radiant panel basically paid for the system. So it would have cost more to put the radiant panel system in than to not do the enhanced window and remove it. So maybe we just skip through a couple more slides here back just to get to the next one. Actually, it's probably the better one that I want to get to. Yeah.
All right.
Just showing that difference, it's about $60 per square foot of window. So that, if you go back to that wedding cake slide, that central piece where the window is, by removing the radiant panel, you're actually saving about $58 per square foot of that window. If you didn't remove it, you'd actually be paying that. So it was a huge budget swing. Just, again, how can you afford not to do this with sort of mentality?
Right. We're on so here's just a picture of the installation. There's just one of the units going in on a cold, I think it was January day, I think. And our last slide here is just some summary thoughts.
Yeah, so I'm going to refer to the items on your left as the selfish owner items. So it was an infrastructure risk. Matt talked about getting into rooms and maintaining them. That is one thing we worry about all the time. There's valves and there's things we have to get at. Access to ICUs are incredibly difficult. But having pressurized water above patient space is never great either. Anytime we can remove water or any systems that could fail and cause what we call a water incursion, it's a huge benefit. So removing those radiant panels was critical. Of course, to reduce operational costs, we don't have an unlimited budget. That's a no-brainer. And I put there a near immediate ROI. As soon as we figured out we had to upgrade the envelope, really, how could we not? It was a no-brainer between, the enhanced and really a standard, because I got rid of all of those things. So rarely do architects and engineers come to us with something like that. From the occupant standpoint is, again, I think Peter mentioned it too. Keith mentioned it. Like, this is what I guess we're really all here for, especially in the healthcare environment. The enhanced patient experience, number one. We always have visitors that are sleeping with their loved ones on that perimeter wall. We give them furniture to do that. You don't know how many times they complain about the thermal comfort in those rooms. They don't complain about the thermal comfort on this floor anymore. Better clinical outcomes. We actually suppress our RH set point, our relative humidity set point in the space down to the absolute code minimum, because we're trying to reduce the condensation issues that were occurring on the envelope. So now we're able to bring those back up. We're able to do what we want to do for the best patient outcomes. And then finally, the healing environment. Uncontrolled water in a building, especially on the walls and behind the cavity, are never good things in a hospital environment. So we really reduced our infection prevention risk in the hospital with the window solution. So I think these are things, especially I'm a mechanical engineer, these are things I don't think of when we're working with an envelope, but it's truly the occupant advantages here were just all due to that envelope upgrade.
So that was the replacement retrofit conversation. Now we're going to get into the reglaze conversation. Before we do that, we're going to do that with Chris. But there's benefits, of course, associated with reglazing, like you have less cost, right? Improved occupant comfort, as we've talked about, even with the replacement. That's true also in the reglaze. Condensation issues with this thermal product that we're going to talk about can help eliminate that issue. With reglaze, you're not tearing out a unit and leaving that open for weeks on end, right? It can be done quickly. So the occupant disruption is minimal, and of course you get higher performance as a result of the reglaze. So this is a reglaze video. Can we play the video?
Hit next. Hit next again.
How's it?
There it is.
So our audio is not real loud, so I can kind of walk you through it. But basically what you're doing is taking everything off of the existing frame, the gasketing, and you're putting down an adhesive on the stems that are there, and then coming in with this thermal product, which is a fiberglass product. On the male-female stack, of course, you have two-piece, you clamp it, and it's there. You're clamping it for about 20 minutes. You're clamping it 2 foot on center. You also do this at the horizontal, as we'll see. You're gonna zone dam it, similar to the way you would install a traditional curtain wall. Run new gaskets. Put the glass in place. Plates and covers. And of course, those plates and covers, the covers especially, can be customized because they're aluminum. So it's a fairly simple reglaze install. And it works very well. We've had great success with it, and Chris is going to talk to that.
All right, so I'm Chris with Studio NYL, and this is, you're gonna see 3 stories that are all before that video was ever made. So it's gonna be a little bit of lessons learned. You know, we heard about, you know, the new build product, which is kind of what we saw in the other retrofit, and we were really into it. Those of you who know us, we tend to use things maybe not the way they were intended to try to achieve the goals of our architects. So in this case, you know, knowing how so many of our buildings are bleeding energy, we were really into the idea of the retrofit. And so, we are finally doing a new version of it. We've done 3 projects at FreMarq and all retrofits. Lee's now working on 101 Tremont here. So existing building stretch code, Reglaze. Anyway, NFRC diagram. You already heard earlier, center of glass is where you get the best performance, whether that's standard IG or VIG, doesn't really matter. Then you start getting edge spacers, framing effect, and you start, you know, seeing losses in your thermal values. So no matter how much better the glass gets, even if we go all the way out to VIG eventually, you start seeing U values going down for the center of glass, even if you do something ridiculous like quadruple glaze, which I've never seen built in my life. Then you add framing factor. Everything jumps. All our U values that were wonderfully low all jumped up higher. And we're losing that capacity. And these are just static ideas based on NFRC framing geometry. You know, bigger glass, better frame. You can start to play with that different warm edge spacers, argon versus air. There's different ways you can tweak all these things, but it all comes back to this simple diagram. So then we were given this building, and the Darth Vader looking like, you know, Javits Center ripoff, leaked in every way you could imagine. Air, water, thermal, everything went through this facade. And it is a basketball stadium. So that means there's very little vision glass in this building. So almost all of it's spandrel. So if glass is a bad wall, spandrel is slightly better, but it costs more and causes condensation problems. So we got involved in a competition to do this, and the initial take on it was there was no chance in hell they could afford to reglaze this building. So I wish I could tell you we did this for some operational carbon good. The reality is we did what we're going to do here because it was cheaper. First thing we did is get rid of all the spandrel glass, because glass that you can't see through doesn't really do us any good. You might as well have a proper wall as opposed to a mediocre wall. So as we started looking at the technology that FreMarq had, you're seeing here, this is their new build construction where they have their own custom aluminum dies that this orange fiber reinforced polymer tooths into and transfers load versus a good thermally broken curtain wall over there. You're getting slightly better performance. You got a lot more polymer going through the thermal line as opposed to a couple of dog bones that are encased into aluminum. And just for frame of reference, fiber reinforced polymer is maybe 1/800th the conductivity of aluminum, because we use aluminum for cookware, right? So polymer is good. And you see the same thing when we do our rain screens, right? This is a poured and bridged Z. This one actually has stainless on it, so it's not as bad as aluminum. Versus a full, you know, Smart CI, Cascadia. I don't own stock in any of these companies, so I don't care which one we buy. But polymer is always going to be better from a thermal conductivity standpoint. So the first thing we did is we're going to reuse all the existing mullions. So one of those cost things that we ran into is we got to demo all the glass out. But what if we don't have to put in new framing? What if we use the existing aluminum mullions for our structure? Aluminum can stand. It's already there. It's been doing it for years. What if I just reclad it with something else? So what you're starting to see in this, what we call our IKEA drawings in the office, is simple hatch channels spanning the 4 to 5 foot mullion to mullion on this project, and the hatch channels are 24 sub center. And it's just your normal sheathing, AWRB, Smart CI in this case, mineral wool, and really the cheapest metal cladding we could get because we didn't have any money. So we now have something that had been spandrel glass to a proper rain screen wall with as much insulation as I feel it. The other thing is, all of it's outboard of the framing, all of it's outboard of the aluminum. There is no aluminum going through our thermal line, and it's all inboard of the AWRB. So now I translate over to reglazing system. The initial idea is we're gonna demo some of this out, we're gonna get some data on what the actual geometry of the curtain wall is, because that's what we were told it was, that's what the archive drawings, so come back in a moment. And then we're gonna design a protrusion that we can then slide over that and fasten into the screw boss. So now we've separated the glass from the aluminum. There is no aluminum going through the thermal line. And just an example from some of the early studies that FreMarq was doing, they were looking at doing it with thin film glass. That's a different story I don't want to get into, but we're going to use conventional IG because we can't afford thin film and I don't want to lose tension on the center film. So as you start looking at the basic geometry again, we start to see what this starts to look like in actual details. Now, one of the challenges we're running into is the glass used to live here. And all our horizontals, we just push the glass out roughly an inch. So we have a dead load there that's now trying to twist all of our mullions. So we have to then be able to justify the existing framing system. The good news on this project, I also happen to be the structural engineer. So we end up putting into our calculations and our documents, in the structural documents, not the A series, analysis for all these mullions that we can justify this, and it becomes part of the design team's scope. I'm not working for FreMarq on this. There are people who are bidding the job for us. So from a delegated design standpoint, when we bid this out, FreMarq owns this polymer out. Everything in board of that, we own as a structural engineer. Here's the problem though. This happened during COVID. There were not a lot of site visits before construction. What we found out is that building was not actually a curtain wall. It was an inside glazed storefront, which means there is no cover cut. There is nothing slide over. So that's what we got. They actually took a sliver cut out of it, sent it to our office. We scanned it, put it in the mass properties, got all the structural data, reanalyzed the mullion. Mullion still works, good shape. Problem is, how are we going to put the polymer on? So as we're talking about trying to come up with some custom protrusion for it, this was already stock. They already own this. And so if you've ever done something like a veneer curtain wall, like FCO, Cornier, Rayco, like you look at H Windows, who's upstairs, that's just a Rayco veneer extrusion mounted to their timber. This can do the same thing, so you guys probably want to talk later and figure out if it's going to perform even better than Rayco. So then we did this, and this is literally what I'm putting in the RFI response, because I didn't have time to draw it. Took the picture, that's my desk in the background, slid it over and go to the contractor, here's what we want to do for this. And he's like, okay, prove it. And I started showing him, these are our standard slides that we use when we try to sell veneer extrusion ideas, because everything below this dash red line is just dumb structure. Everything above the line is the intelligence. It's our thermal breaks, our air and water. It's how we delicately pick up the glass. And then as you go from these aluminum systems here to steel or timber, we can do whatever we want. So in the same sense, in this case, whatever we want happens to be the aluminum mullion that's already in place that we don't have to buy, we don't have to demo, we don't have to install. And of course, similar slide just showing the thermal. This is showing a traditional, like standard, and Cornier, YKK, whoever, thermal, you wouldn't see that in a polymer-based mullion. And we do this all the time. I haven't done one of these yet with the polymer veneer, but these are all veneer curtain walls. So we tend to trick this out a lot. Back to our particular project here, comes up with a couple other problems for us, in that, as you see, the glass used to live here. There's no cladding on the existing building. There's cladding over this. So as you look at that existing mullion, cyan's covered. We now have to cover this kind of peachish looking color, I guess. This is something we had to reclad, and then the green, because sustainable green, that's the new polymer protrusion that we put on the system. So there was a little bit of extra work we added on the fly as we were going, and then you see it's done. So there were a couple extra lines that we had to deal with, but these are some of the things we contend with as we retrofit it. And just some of the imagery of it. One of the things I did get rather upset with Todd about is you can see different colors for this. This one's black. This was a soy-based polymer at the time, and they changed it. And I'm like, you're killing the carbon story. This was the great material. It's made soy. He gave me the LCA for the new one that was not soy-based, and it's actually better than the soy-based one. So it's actually a low carbon material, especially when you're comparing it to the equivalent aluminum, which is a very high energy intensive material. And there's the building done. It is not going to be the front of the brochure look at me project, but from a performance and embodied carbon story and a budget story, it's really quite amazing. And and I said embodied carbon, operational carbon is probably better than embodied. So we did it again. This time it's the Denver Performing Arts Center's Buell Theater. This was a monolithic glass. Oh, that's really bright in my face. So you can see these are shots from the archive documents for the building, and we side by side them. This is right from our construction drawings, on the structural drawings, mind you, showing what we're going to be doing to each of the mullions based on the archives coming out. So I'm just going to flip through a couple so you can start to see. Here's the detail. We went back to the drawing board initially. We're going to do the original way of planning it. We're going to try it again. And what we started finding out is the screw bosses on each of these mullions was the same. Apparently, they bought some of the mullions from a different fabricator. And so I'll get to that slide in a minute. One of the things that often happens with these reglazes, which is challenging, is they don't have the budget for all of it. So we were not replacing the skylight, but we were replacing the vertical wall. Column covers were not being replaced. So how do we start to not just move our condensation line to somewhere else where it's just going to drip 3 inches over, and trying to figure out what we can get away with our budget to try to get some better insulation. You're going to see in a little bit, but the theory is going to be, if you don't measure, you can't manage it. So it turns into a lot of analysis. Not that I'm trying to turn this into a jobs program for facade consultants, but it sometimes does turn into that. So this is the elevation of the building, historic layout versus what we end up doing. You notice we added an extra mullion in here because we couldn't afford the oversized glass. This is a massive piece of glass, and you know, at the time it was monolithic. So here's our proof of concepts that we started doing, coming in with the system. U values for this started out with the FreMarq system because that's what we really wanted to do. And they said, we don't think we can afford it. Oh, the other thing is we had to hit 0.38 because our system U value is 0.37. So the first thing we looked at is, you know, the standard logical thing. The easiest way to avoid a thermal bridge is to eliminate anything going through the glazing line. So we went to structural silicone. And what you're seeing is the red's bad. We're actually over the value. And a lot of it, what people don't realize is a good captured system is generally going to perform better than an SSG system. Partially because of the density of the structural silicone versus a gasket, but also what is the glue line thickness of your structural silicone. So if you are doing an SSG system and you're not seeing the numbers you want, make the dimension from inside face of glass to outside face of aluminum just a little bit bigger, and you can start to tune that U value. So I know this is supposed to be about the polymer system, but this is the trick we go to all the time. So as a result, we started looking at tweaking that out, using better glass, and we were able to get the SSG to work. But to be fair, is when we switched to the better glass, what did it do with the FreMarq system? So we're still 600ths better than the SSG. Plus, we didn't have to worry about holding the glass up in place, temporary works. I mean, this is an existing theater complex. This is one of 5 theaters that all use the same outdoor pre-function space. So closing it down for an extensive period of time is going to be a problem. So once again, we get back to the diagrams. Like, well, this is too expensive. So we go, oh, well, this is what we did at West Carolina University. And so once again, a lot of high-tech drawing here. I just blue beamed right over. I was like, well, what if we just put a spacer in there and use the same existing polymer protrusion that we had before and mount it onto this? And that actually ended up saving us a lot of cost because we didn't have to demo the glass early and verify what was there. We knew that this was going to work because we could already measure what the width of the mullion was relative to this protrusion. And then it's just a matter of spacing it out and getting it. This time we were able to plan ahead, so the spacers were aluminum, so we didn't have to finish them because they were already finished. And then now we start getting into shop drawing levels. So now we're going to get all of our U values more specific for all the unique glazing systems around the building, including the doors. So once again, you can't measure it, you can't manage it. I must admit, this is showing you the U values for the system, but most of these studies were more about what happens at edge of system. How do we avoid the condensation right beyond our scope of work and do that transition appropriately? What is the drying potential, things of that nature? So I'm trying to go fast through these so we can get to the punchline. So you can see, obviously, different size glass, different amount of openings. You get slightly different U values with each of the systems, but they're all coming in well below 0.38 that we have to. And I realize we're in Boston, 0.38 is garbage to you guys. But think about what we do when we do this with triple roofs. So it's the same basic idea. Like when we're doing it, what's the number of tray mount? What do we hit? 0.25. So once again, there's the polymer just sliding over. There's the finish. They did, put the little bit of glitz on the theater by adding some LEDs on the cover caps. All right, and there's one more. So this one's not done. So this one, I'm going to get caught up in more stories eventually of what didn't go right. But this is a building that was, at the time, really adventurous, and probably before the technology was available. This is the architecture school at Ball State University. And it was kind of a cross between double skin and a trombone. However, it was on a slope where the inside of it kind of serrated with the truss. So from an airflow standpoint, without the benefit of CFD analyses, the air doesn't move. It turned into a massive dump of hot, wet air that ended up condensing all over the building for the last 30 years. And we're finally going to do something about it. So we went through a lot of different options. I don't think I have them all on here. Square it off, add square footage, add program, lots and lots of ideas. And of course, as always, seems to be my theme, we couldn't afford it. So here's the existing building. You see the slope there. Yeah, and some of it's solar thermal, some of it's glass with the double skin trum, and some of it's just a skylight. So it's a couple of different systems. And this is what we ended up coming up with. So it's like the same thing as Western Carolina, but on a slope and a skylight. So here you're starting to see a reenactment of the existing. I didn't see the fancy new video yet, so we're still going with the spacers. I decided that's the way we're going to go, so we don't end up over torquing the existing. But one thing we did add is this, even though it's a high performance thermal system, we decided just like any good skylight, we could add some brake metal to add a condensation gutter underneath it. So if there ever is any kind of drip, we have the ability to manage it. And here you're starting to see it in section. And then we got rid of the glass. I mean, this thing is an oven. It's east facing, if I remember right. So it's just baking all morning. It's kind of like the GSD. It's multiple levels underneath the skylight, all exposed. So hail guard, roofing membrane. And then what we did is we created kind of a poor man's rain screen system. We put a hat channel over it, fastened it down through the membrane, and then ran another layer of membrane over it. The trick on this is you got to size the hat channel such that the screw with the metal panel coming into it, with the self-drilling tip and everything, is short enough that it doesn't penetrate the membrane. And it only took 2 reviews in the shop drawings to get the screw the right size. So that will be fabricated soon. But simple, dumb, low tech. Oh, I left out. We're actually just spanning a simple 1.5-inch metal deck mullion to mullion. So you think of like a standard Volcraft roof deck that could span 5 feet. Well, instead of bar joists, we're mounting it on the mullions. Same basic idea, just a little bit of similar metals issues to deal with. But now we've got a proper roof instead of what had been a skylight that we did. Just a couple more of the details. These are a bunch of brass handiwork of transitions. You notice our thermal line kind of cuts straight across, more or less on these. As much as we can do to get the inside face of that insulation as close to the inside face of glass, really helps those transitions quite a bit. Maybe see it zoomed in a little bit more. It's not quite perfect. I mean, we're sitting up a little bit because of where the metal deck was, being 1.5 inches. That's close. There's a couple more shots. And then here's the kind of slide that Todd was going to talk about, the lessons learned that kind of is informing that video you saw. So what had been this, which takes field measurement, survey, etc., custom die, pultrusion, we evolved to this where we said we're going to shim it with cheaper material. Now what they've done is they've done a pair of angles. They then mount over it, and then they're easily adjustable for multiple things. If you're asking, I'm a little frustrated, I didn't know about this when I was doing Skyline, of course I am. But it would have been harder to do the condensation. But the idea is this is constantly evolving and getting better and better every time we build one of these projects. And this methodology of doing it is just making it easier and easier to build. Because the lower the labor gets, the better we're going to do with this stuff. Am I out of time? All right, we're on question.